Hello, my name is Henriette Wirth and I am a PhD student in astrophysics at Charles University and a former software developer. The cluster you see on this screen is not real. This is a simulation I did with this program PITAR, and like PITAR, we have a number of software packages in astrophysics that one can use to simulate various things. As a scientist, you are likely to have to write your own software one day. So the question becomes, how does one design a scientific program? Now, to answer this question, I want us to first ask ourselves, who are modern programming languages written for? We all know programming languages, which are basically a means that we use to explain a process to a computer so the computer can execute. But are they really still written for the computer? I would argue no, because this is what a program would look like if we really just wrote it for the computer without any consideration for the human behind it. Some of you might be able to read this. However, I think we can all agree that if we would force scientists to write their software in this way, it would go down very, very badly. So, if we know that programs are a means to explain a process, and we know that programs are designed more for the human than for the computer, we can ask ourselves, well, what makes a good explanation for a human? And for that, I brought a little example. If you are in astrophysics, you will know these proton-proton chains. If you are not, you might think of another process happening in your field. And just imagine you wanted to take this process and explain it to your grandmother who doesn't know anything about your field. You can pause the video now to try to think of how you would go about it. If I was to explain this process to someone, I would start with, hey grandma, you know how stars emit all of that light? The energy for emitting this light comes from what we call proton-proton chains. These are processes happening inside of the star where hydrogen atoms are fused into helium atoms. And then I would go through all of the details, all of the individual steps, depending on how far I would go. Now, the thing I'm getting at here is that if we are explaining a process to another human being, we usually want to start from the general ideas and then focus in on the details while making sure that the person we are explaining something to always knows where in the bigger picture they are. So, how can we translate these ideas to the software that we are writing? Well, in each program, I use here, for example, the Python programming language, but you could also translate this to other languages. In each program, you will have some kind of main file, which will contain the very first lines of software your code will execute. And inside of this main file, you can find the main function, which should be the only function contained in this file. And this function just contains very generally the different parts of your program. So if you look at this function, you see that to run this program, it will initialize something. It will then run some simulation or do some calculations, and it will at the end produce some kind of output. Now, then you would probably do subfiles for these different steps which contain more details. So for example, I might have a file called init.py, and this file then contains the initialize function that I call from the main function. And if I look at it, I see that, okay, to initialize the program, my code reads some kind of config file and it reads some kind of data, maybe also from a data file or from some other source. And if I have a particularly large software package, I might even want to separate it out further. So I might have a separate file for reading that config file, which contains all the functions needed to read that config file. Now, the question here is, of course, well, how long do you actually make these individual files and how long do you make these individual functions? And I looked through some of my recent projects, and what I found was that in my case, the average function length is below 10 lines. This does include a lot of functions that have only one line. And it makes sense to make one-line functions for two reasons. One is bugs. You will have bugs in all of your programs. And if you have a line that's a little more complicated and you miswrite something, then you will have the bug only in one place and not somewhere else where you call the function. And it's very easy to fix. The other reason for it is that you might want to update your program later. So in one of my recent projects, I used the correlation between the initial density of a stellar cluster and the initial mass of the stellar cluster. It's a very simple one-line correlation, and I wrote it into a separate function. Now imagine my supervisor comes to me and says, "Hey, Henriette, look, we found out that actually this correlation is slightly different. Can you please redo your calculation with this new law that we found?" If I would have copied that law into all of the places where I needed it, then I would have to go through the entire program and change that line everywhere. While if I only have one function where that law is defined, I have to change it in one place and I'm happy and I can just do my calculations right away. Now, this is for function length. When it comes to file length, what I found was that my average file length varies much more between projects than the average function length. And I have somewhere between 60 and 120 lines, where the 60-line program was a program where I made a graphical user interface. And the 120-line project, that was something that was a little more math heavy, where I did a little more difficult algorithms and things like that, which did take up a little more space. With that in mind, I would like us to do a little exercise. Let's say we want to design an n-body code, like the one that simulated the cluster you saw in the beginning. So let's say we have some kind of input file that already contains the initial masses, coordinates, and velocities of all the stars in our cluster. So we just have to read it in. After we read in the input file, we have to compute the forces between the various particles, and we will have to move the particles according to these forces. And in the end, we want to output the stellar masses, but not only in the end, we want to output the stellar masses, coordinate, and velocities at regular intervals during our simulations so that we can see the development of the cluster. And if you like, you can pause the video here, take a pen and paper and try to plan out the program yourself. If you don't, then I will show you how I would separate out this program into different files, which I also call module oftentimes. So you definitely would want to have a separate module to read that input file. And analogous to that, you might say, okay, we want a module to write the output file. Then I said we want to compute the forces between the stars. So I would make some kind of force calculator here. And we want to move the stars. So we need a particle mover. What I would also want to have in my program would be some kind of scheduler that just takes care that everything is done in the order. So the output might be done every 10 time steps. So the scheduler takes care of that. And of course, it triggers the calculation of the next time step. And then, of course, we have the main function. Now, after we have all of these different modules, we want to ask ourselves, how are they connected with one another? So we do want to maybe read the input file from the main file. We also want to initialize and run the scheduler from the main function. Now, the scheduler, as we already said, is to trigger the output in regular intervals. And we might say, okay, we also let the scheduler trigger the force calculation and the particle mover. Now, if we do it in this way, this will work well if we have, for example, a simple Euler forward integration scheme. Now, the purpose of the Euler forward method, as most of you will probably already know, is to compute a time variable. So, for example, here we might have the coordinate of the start or the velocities. It will then compute the tangent to the function at time step t0 and just follow it to estimate the value of the variable at time step t1. However, we might say, okay, this actually creates quite an error here. So we might think about using a more sophisticated method. For example, we might use the Runge Kutta 4 method. I am going to link a video that explains this method in detail in case you haven't heard of it. What I want to get here is that this more sophisticated method actually doesn't only require us to calculate the derivative and therefore the forces at this time step t0, but also creates these intermediate time steps where we also have to calculate the derivatives. So now we have to compute the forces multiple times per time step. And these derivatives are then put together to find a point that is usually much, much closer to the real curve that we would see if it was just the cluster we see in reality. Because we are now computing the forces so often, what we want to do is that we want to attach the force calculator to the particle mover and not to the scheduler anymore. This means that we can switch out the particle mover more easily because, first of all, if we switch from the Euler forward to the Runge Kutta 4 to any other integrator, the way we calculate the forces doesn't change. So if we decided to upgrade our particle mover, it wouldn't make a difference for that. And if we let the particle mover decide when to calculate the forces rather than the scheduler, that means that with every upgrade that we do for the particle mover, we do not even need to touch the scheduler. So we can really just update our program by changing only this little part up here. And if you design your programs, I would always recommend to keep in mind how you can separate out your program in such a way that the units are as independent of each other as possible. So if you do changes in the future, you really have to touch as few modules as necessary. We now have planned out our program. There's only one thing that we might want to put into a separate file, and that is the data. So after we read in our input file, we will, of course, have to store our stellar masses, positions, and velocity somewhere. And this data is then passed through the programs from our read input file module. Now with that, I want to end part 1 of this course. And if you're interested, you can look into the second